Okay, so last time, the main thing we talked about was the fundamental group of the circle. And we discussed why the fundamental group of the circle is isomorphic to Z. So let me just briefly recall the highlights of this. So I'll break it up into 3 steps. So step 1 was the path lifting, which says that given F some loop in S1 based at base point, so loop based at 1, there exists a unique path F tilde in R. Sorry, my pen is being a little slow to respond. With the property that, so this path starts at 0, and so F of 0 is 0, and it lifts the original loop. Which means that if you do P and then F tilde, you get F, where here P is the map, the exponential map from the real numbers to the circle. So given F, you can find a lift F tilde like this. Okay, so that was the first, and I would say the key ingredient. So then step 2 was to use this map to define a homomorphism. So define phi from the fundamental group of the circle to Z by sending a homotopy class of F to the lift of F at 1. And as we explained, this is well defined independent of the representative you choose, and it's valued in Z because the endpoint of the path ends at a pre-image of the base point 1. Right. And this is a homomorphism, as we discussed. And then the final step is that phi is, we showed phi is bijective. Okay, so this is the rough outline of how we prove the fundamental group of the circle is Z. And the main thing we haven't discussed is why this path lifting statement is true. So we saw a bunch of examples last time, but we didn't give a formal proof. So let's do that now. So let me just keep this statement up. All right, so proposition. And let's just erase this too. And move this up. All right, probably can't see the whole statement, but okay. All right, so, okay, sorry, proof. Let's fix F some map, and we'll define the loop. So, right, so the first step is something we showed before. So from last week, there exists a partition. We can partition the interval into subintervals. Some finite number of them, so that the image of each of these is contained in some, let's say, open hemisphere. Or hemisphere, we're on the circle, so I guess I can just say semicircle. And say U, I in, let's just say U in S1. So the picture, we have the interval mapping to the circle by F. And so we gave an argument last week that you can break up this interval into little pieces so that subintervals, so that each subinterval maps. So here's the interval AI to BI. AI and BI are contained in some hemisphere, or F of AI and F of BI. And the path also stays inside of some semicircle. So here, the semicircle here might be something like this. That's U. Okay, that's supposed to be BI, if you can read it. All right. Okay, so let's see what we can do with this. This is going to aid us in defining the lift. We'll define the lift over these subintervals separately. So in order to do that, first an observation. So observe that, so if we take U, one of these semicircle subsets, so we could write it as like points E to the let's say 2 pi I t, where t is between some theta naught and theta naught plus pi. So it's a semicircle on the circle. And so for U like this, the pre-image under the map P the pre-image of U, well, what does it look like? It's a union of intervals in R. So so like if we take this thing here, then what we have is a union of little intervals like this. I mean, the map P is of course periodic. And so here's U and here's P inverse of U. And we can write it in a formula as, so we have the interval theta naught to theta naught plus pi, plus, no, I guess upstairs that's theta naught plus a half. And it's a union of these. You have all the translates of this. So, well, shouldn't have written that first. So theta naught plus n to theta naught plus 1/2 plus n. Disjoint union over n and z. Okay, so you have the original theta naught to theta naught plus a half, and then all the translates. And so that's what we have pictured here. Okay. And so now what we'll do is we'll define the lift, F tilde, inductively, and right, so that works as follows. So suppose F tilde is defined on AI. So then define F tilde on the interval AI to BI as follows. So let me first draw a picture again. Or maybe I can use this picture, although the part of it is a little small. Let me make this a little bigger and work with this. So right, so we have some segment, the image of AI BI, which does something here. And so here's F of AI as before and F of BI. And then we have the pre-image upstairs, which is a union of these intervals. And we're assuming F tilde of AI is defined. So F tilde of AI, it's in one of these intervals. So F tilde of AI. But now the thing is, there's a topological equivalence between the interval, the red interval containing F tilde of AI and our original U. And so if we want to define the lift, well, we should just compose F with this topological equivalence to get, whatever the map should be. So how to say this exactly? Yeah, so let's write F tilde of AI. Let's suppose it's in one of these half open, or these open intervals, like theta naught plus n to theta naught plus 1/2 plus n. So this interval is topologically equivalent under the map P to U, the restriction of P. And so let's write R for the inverse map. Okay, so I guess I have to write this again. Of P restricted. So now define F tilde of T to be P, R composed with F of T. This is for T in the interval, closed interval from AI to BI. Right, so the only thing that we should check, well, so observe that F tilde of AI is, so let's see, what do we do? So we do F of AI, and then we do R, but this is a topological equivalence. So, this map does what we want on AI. Maybe I shouldn't write that. Well, yeah. So F of AI is already defined. So the thing is, we want whatever is on the right-hand side to agree with what we've already defined. So F tilde f tilde of AI is already defined. And on the right-hand side, there is exactly one element in this red interval which contains a preimage of f of AI, and that's exactly the point f tilde of AI. So the left and right-hand side agree on AI. But then, right, and this map is a lift, so note that P compose f tilde of T, so this is P compose R compose f of T, but P compose R is the identity, so that's f of T. So f tilde is a lift of f, at least on the interval AI BI. Right, and so this is the construction. So so note that f tilde of 0 is 0 starts the induction. Okay, so this is the construction of the path. So you just do it inductively, and you use this property of the map P. Well, yeah, that if you're in some, well, okay, maybe I won't say the whole thing again. So there is one other issue that needs to be discussed, which is the uniqueness here. And well, let me just say a word about that. So uniqueness claim is that there's this f tilde is the only f tilde that works, that satisfies the conditions that f tilde of 0 is 0 and that it's a lift. Well, okay, so just observe that we didn't make any choices. So at each time, our hand was forced. I mean, for any point, so maybe this might be helpful. So at any point here, so at any time t, you have f of t, and you have choices for what f tilde of t is going to be. And it has to be something in the preimage. It has to be something that maps to f of t downstairs under p. But ultimately, the map has to be continuous. So if you've already defined the lift for points near t, then there's really no choice for how to extend it to t. So okay, so this is a rough explanation for why you should believe the uniqueness. Okay, and then that's the proof. Right, so a remark, which I kind of started to say a second ago. So there's an important property of this map from R to the circle. And it's an important enough property to warrant a definition. So this property motivates the following definition. So we say a map P from X to Y is a covering map if for every little y and y, there exists an open set U containing y, so that the preimage of U is topologically equivalent to a product of U with some discrete set delta. So in the case of R mapping to the circle, we saw that for any point on the circle, you could put that in a little hemisphere, and the preimage of that hemisphere or semicircle is just a product. It's a union. Well, so it's a disjoint union of sets topologically equivalent to U. And here, in this case, that discrete set is Z. So there's Z many copies of U. And right, so this is the key property that we used to do the path lifting. And you can prove a similar path lifting whenever you have a covering map. Yeah, so, well, we might discuss this a little later in the course. So e.g., the quotient map from the two sphere to RP2 is a covering map. So actually, we've seen a lot of covering maps in the course already, but okay, that might be a later topic. So now in the remainder of the time, I want to give some applications of this computation. So the computation of the fundamental group of the circle turns out to be an extremely useful and important computation with lots of applications. So I want to just explain a few of those. Right, so the first, yeah, and actually we'll see a lot of these applications over time. So this is just maybe the tip of the iceberg. So first, another computation we can do now is the fundamental group of the torus is isomorphic to Z squared. So this follows from a more general proposition that the fundamental group of a product of spaces is isomorphic to the product of fundamental groups. So, right. So here, to apply that to the torus, we have pi1 of the torus. This is pi1 of the circle across the circle, which is isomorphic to pi1 of the circle times pi1 of the circle, which we just computed. And so that's Z times Z. Right, so for the proposition, I am not going to prove it. You can read it in Armstrong if you like, but let me just explain why it's true or tell you the setup. So, and then you can fill in the details or read it in Armstrong. So if you're given any loop, so let's say this is a loop, let's say based at some point PQ in the product. Well, you can write F in coordinates. So you can write F as F1 comma F2. Where here, F1 and F2, they're exactly loops in X and Y. So given this, you can define homomorphism from the fundamental group of the product to the fundamental group, the product of fundamental groups. I should write the base points, but I'm not. So it's sending the homotopy class of a loop F, which we write in coordinates like this, to, well, to this element in the product. And you can check that this is a homomorphism. It's a well-defined, and it's an isomorphism. It's a good exercise to do. It's so good that I'm going to leave it to you. All right. But in particular, we see for the torus we know exactly what the generators are. So this identification with z squared, that's the fundamental group of the circle with the fundamental group of the circle. So we know what the generators for the fundamental group of the circle are. You have a circle in this direction, and then you have a circle in this direction. Well, that's not much of a circle. So where one coordinate is kept constant. So so you have like f of t is e to the 2 pi I t comma 1, and g of t is 1 comma e to the 2 pi I t. These generate pi 1 of the torus. Okay, so I guess in my picture, maybe this is G and this is F. Okay. Okay, good. So we know the fundamental group of the torus. This was a computation we discussed informally previously. Another corollary is R squared is not topologically equivalent to Rn for n greater than 2. And let me just remind you that we already proved that R2 is not topologically equivalent to R1 using connectedness. And okay, so let's do the proof. So for a contradiction, suppose R2 is topologically equivalent to Rn. So we fix some n at least 3. So then, well, so the proof is going to be similar to the proof that R2 is not topologically equivalent to R1. But instead of connectedness, we're using the fundamental group. So, well, okay, so first of all, then if this is true, then we can remove a point and still get a topological equivalence. We've seen this argument. But okay, and now here's where the circle comes in. So R2 time without the origin is topologically equivalent to the circle times infinity. This is like polar coordinates, I guess, or well, in a picture, if we remove the origin, then well, every point is on a circle of some radius. And the same is true for Rn. This is topologically equivalent to Sn minus 1 times array. It's like spherical coordinates. So then, this means that the fundamental groups are isomorphic. So we proved that last time, that the fundamental group is a topological invariant. And well, okay, so now remember this proposition, fundamental group of a product, we just split it off. And the fundamental group of array is trivial, similar to the proof that the fundamental group of R is trivial. So this is isomorphic to the fundamental group of the circle. And this is isomorphic to the fundamental group of the n-1 sphere. And so we know this is Z. And since n is at least 3, we know this is 0. So we computed that last week. Okay, and then that's a contradiction. Okay, so this is exactly why we want topological invariants. They let us prove things like this. They give us a tool. They give us tools to show that spaces are different. Okay, great. And I mean, you should take a second to just appreciate there was a lot of work that went into this. I mean, it took some work to compute the fundamental group of the sphere and of the circle. And yeah, I mean, even though you might think that this corollary is obvious, R2 is not the same as Rn, it does take some work to actually show these things rigorously. And moreover, I mean, sadly, this doesn't even show a statement as general as you'd like. So remark, this argument can't show that R3 is not topologically equivalent to R4. So that's a little disappointing. So typically the tool for showing this is homology, which I think we won't discuss in this course, but okay. All right. A couple more corollaries. Right, so the next corollary is called the D2 retraction theorem. So let me just tell you what it says. So this is about maps. Yeah, so let me tell you what it says before saying anything general. So there is no continuous map from, let's call it R, from the two-dimensional disk to its boundary circle with the property that R restricted to the circle is the identity on the circle. Such a map is called a retract. That is, if you have a subset of X, and there's a map R from X to A, which is the identity on A, that's called a retract. And so the corollary is saying there's no such thing for the disk and its boundary circle. So this is a different kind of corollary than we've seen before. And this is another sort of way that, I mean, this is, this falls into another general class of topological results. So I mean, here we have the circle including into the disk, and well, we're just wondering whether or not there's some map like this so that the composition is the identity. So here's the inclusion J, and we're wondering whether or not there exists some map R. So I'll indicate whether that we don't know that this map exists with a dotted line. We want to know if there's a map like this. And topological invariants are useful for showing these kind of, for studying these types of problems. And to illustrate that, let me just tell you the proof now. So proof. So let's okay. So suppose R exists. So we're going to do this by contradiction. So then, well, R composed with J, as in this diagram, is the identity on the circle. This means that R composed with J, the induced map on fundamental groups, is the identity, or is the induced map of the identity. Or I guess I mean to say, let me rewrite this. So, okay, so this step is just using the functoriality that we mentioned last time. So the composition of the induced maps is the induced map of the composition, which is by assumption the induced map of the identity. And we showed last time that the induced map on the identity of the identity function is the identity on fundamental groups. Okay, so now we're almost done. We're basically done. So this is very problematic, and let me explain why. So we have this composition of maps of fundamental groups. We have pi1 of the circle mapping to pi1 of the disk, mapping to pi1 of the circle. And so here's J star, R star, and the identity star, which is just the identity. And we know that this composition is the identity. R star composed J star is the identity. But the problem is, okay, so this group is Z, this group is Z, and this middle group, this is trivial, as we've seen. And well, now this doesn't make any sense. We have the identity map, which factors as through the zero map. So, so let me just say it this way. So since pi1 of the disk is 0, the composition J star compose R star is 0. But J star compose R star, as we argued before, is the identity, and the identity map on Z, and that's a contradiction. Okay, so all right. Right, so final thing, final application, and this is a corollary to the corollary. And this is called the Brouwer fixed point theorem. And it says that any map from the disk to itself has a fixed point. Has a fixed point, which is to say there exists an x so that f of x is x. Oh, I'm going to call this map phi. I could call it f. Yeah, no, it's fine. I'll call it f. All right, so proof. So suppose all these proofs go by contradiction. So suppose f exists. That is, there exists an f with no fixed points. And so the strategy is given, so this is a corollary to the corollary. So given f with no fixed points, we want to construct a retract, a continuous map from the disk to the circle, which is the identity on the circle. So here's how we'll do this. So we define R from the disk to the circle. So I'm out of space. Let's do this on a new page. Yes. All right. So this is going to be short. Let's see how it goes. So right, so how do we define this map? So let me draw a picture. So, wow, my pen is being slow. So given a point x, by assumption, we have some point f of x, which is different from x. And consequently, we can draw a ray from f of x to x, and that's going to meet the circle in a unique point, which we'll call r of x. Okay, so this is going to give us a map from the disk to the circle. And notice that, well, we claim that R is a retract. So okay, let me just write. So R of X is the intersection of the ray from f of x to x with the circle. Yeah, I guess it's clear if I put the circle first in this sentence. Intersection with S1 of the ray from f of x to x. So what we need this map to, we need the map to have the property that it fixes any point on the circle. And so let's think about what happens if we chose x to be on the circle. So again, f of x is some point other than x. I mean, it could be some other point on the circle, or it could be some point on the interior. But in either case, it doesn't really matter. So we draw this line, this ray from x to f of x, and we see that it intersects the circle exactly in x. So it is indeed a retract. So then R is a retract, which is a contradiction.